Our next speaker is Karl Pazdernik, who is a senior data scientist at Pacific Northwest National Laboratory in Washington State. He's a senior data scientist and team lead, and he has a joint appointment as a research assistant professor at North Carolina State University. Please welcome Karl.
Thank you. Thank you for allowing me to speak today. And first, I want to start by acknowledging all the people who have worked on this project over the past few years. So this has been a very collaborative effort with staff at PNNL, faculty, and a student at North Carolina State University who is here with us, Andrew Halls, and has successfully defended. So congratulations, Drew. And a student and faculty at the University of Michigan. Okay, so first I want to talk about, what is our motivation for this problem? Really, we're building language models for the nuclear domain to aid nonproliferation. So the first step of this is really understanding the scientific literature within the nuclear domain. I kind of see this as like a three-step process. First step is really to triage your information to basically subset your corpus. So there's a lot of scientific literature out there, and we don't want to analyze all of it, mostly just focus on the relevant articles. The next step is then to understand our subset. Once we've subsetted the corpus to what we're interested in, how do we define what's in there? And then finally is the task of really prediction. So once you can kind of subset the space and define what's in there, can you actually predict what's going to happen next? Now, for the purposes of this talk, I'm mostly focusing on the first aspect of this, which is just triaging the information. And so that really involves identifying nuclear relevant research. And we're going to do this primarily through document classification. All right, so a little bit of prior work here. Something that we first started with when we were looking at this space is there are lots of large language models. Now, this was a few years ago, and so obviously this space has changed quite a bit in the past few years. But at the time we were looking at, all right, how well do these solutions, these off-the-shelf solutions perform for these tasks, which, even at that point is still impressively well. But we also know that the data used to train the model has a very direct impact on its performance, on the inference, right? As the previous speaker was mentioning, as soon as you get out of distribution, you expect the performance to degrade quite a bit. So what we wanted to do is we build these domain adapted models, which is really refining the set that you're training on and then having your language model basically learn that domain. We did it as a two-step process, which I'll go into in a second. After that, you can then explore any subset of the corpus through things like topic modeling. And then you can build a graph that is a co-authorship network, and you can basically explore the evolution of these collaborations over time, and even do so in a way that incorporates the information of the topics in the corpus in that network. Okay, so focusing on language models. So the first thing we want to do to build a domain adapted language model is the step of pre-training. So when you're talking about these deep learning models, there are many parameters in the model that can be tuned, and there are different ways to tune them. So we basically employed the approach of pre-training followed by fine-tuning. So the pre-training task is designed to get the model to just understand the domain, not necessarily for any particular purpose. These models are usually trained by essentially removing a word and then predicting that word, or the more generative models where you essentially predict subsequent words and basically predict a full sentence, paragraph, and so forth. So this is the first thing that we did. We started with a few base models, foundational models, such as Roberta BERT, SciBERT, which was trained on scientific literature. And we had a set of documents from OSTI that are going to be a little bit more tuned towards the nuclear and energy domains, like that is what the subset is. And then we looked at basically evaluating that loss function based off of removing that word, removing a single word and predicting it. That's the mass language model loss. All right, so just from a first standpoint, regardless of what base model you use, yes, if you do continued pre-training with the right corpus, you improve your MLM loss, as you can see here. And you can evaluate this in terms of interpretability too, like actually looking at what words it would predict when you remove one, and they're much more intuitive within the nuclear domain. Okay, so that was good. That was useful. But of course, we want to then apply it to the task of classification. And so that's where we do the fine tuning. So in OSTI, there are already labels that are provided. There's 99, although only 60 of them are really currently being used. And so we have we have our training data, we have labeled data, which is particularly nice. That isn't always the case in the real world. So we trained a multi-class model that tried to predict these 60 labels, and secondary, a binary nuke or not nuke model. Now, the binary nuke or not nuke model was following basically these IAEA physical model categories of which of these 60 labels are related to the nuclear fuel cycle. And so there's a handful of them, I believe 9. Okay, so how does this pre-training followed by fine-tuning, what is the impact of it? And so you can kind of see here, just off-the-shelf models don't have the plus OSTI, and then the nuke LM model here is the Roberta Large plus fine-tuning with, or plus the pre-training with OSTI. And so you can kind of see that model produces the best classification if you're looking at just overall score of F1 score. Generally, it performs better across the board of metrics, accuracy, precision, recall. The binary classifier actually had slightly better precision on the Cybert with the fine-tuning of OSTI. And I'm not necessarily one to go metric chasing, as you would say. Is all of that extra effort of training worth minor points in F1 score? Sometimes not. In this case, if you're thinking about, the number of articles that are published every month or year, the scale can actually be quite a bit. So you're actually looking at even a few percentage points in F1 score can greatly impact the number of articles that you would use in your refined your corpus when you're actually doing downstream tasks. Okay, so we basically decided this is a useful task of adapting these models to your domain, doing the pre-training, doing the additional fine-tuning as well. But we wanted to explore that a little bit further, and so we looked at, okay, this was a situation where we had pretty good data. We used a training set of almost 200,000 documents, so that's a pretty good space to start in. But we also know that these models are brittle. They're not always reliable at each iteration. If you change the initialization and retrain it, you can get slightly different and sometimes drastically different results. So we wanted to see, okay, well, what else does this process of pre-training and fine-tuning actually provide us? And so we looked at doing the same task, but with a reduced number of samples. So just the fine-tuning task, now we're not giving it the full 200,000 documents, or almost 200,000 documents to tune on. And what we noticed is, okay, so certainly, as you can kind of see here, the distributions between nuke LM and Roberta Large, yes, the loss is decreased by using the nuke LM model pretty much across the board, regardless of how much data you give it. But what we really noticed is as you have a smaller and smaller data set, the difference is accentuated. Yes, the mean of the distribution is lower, but where the mode is quite a bit different. The spread can be different, and so we're looking at this now from a perspective of we know that this approach can improve our overall model performance. But when we're working in the space of nuclear nonproliferation, these are, is a pretty high stakes environment, and we're doing inference on single documents. You're predicting the class of a single document. So what is the uncertainty in that single point prediction? Can we quantify it? Do we actually understand what we're getting when we're getting out these scores that actually translate to a classification? All right, and so then this brought us to the second portion of this work, which is the uncertainty quantification in text classification. All right, so for us, what is important for uncertainty quantification? Well, for one, if we want to actually deploy these models and have analysts use them in near real time, they need to be computationally efficient. We can't have something training for days or have inference that takes that long as well. They need to be calibrated. So this is kind of one of the main problems with these models, just generically off the shelf. If you take the scores as they're reported, you might get a score for a class. The highest class is like 0.98. And then you see 5 documents that come out with a score above 0.99 and only 2 of them are correct. That doesn't really match our intuition. And finally, for single point predictions, we want, or not finally, but for single point predictions, we want good coverage, which is basically if we are predicting a particular class for a document, what are the other classes that also have some probability, some higher probability associated with them? And we want, this is, like a more standard statistical concept. We want the coverage rate of this credible set kind of match our threshold, our predetermined threshold. And finally, interpretable. So what we often notice is that you might get a single, the most likely class has a pretty high probability, and then the other classes that have lower probabilities might be almost seemingly random at which other class is selected. But that doesn't really make much sense with our intuition of a document. If we're not sure if the document is in nuclear fuels, but we think it's kind of in that space, is it going to be in cell biology? Probably not. Probably something still more related to nuclear physics, atomic physics, something of that nature. All right, so we then defined from those goals of the 4 things that we wanted our uncertainty quantification to include, we need to kind of define a metric for each one of them. So first is efficiency, and we've put some bounds around this. Obviously, you can always throw more compute at problems depending on where you live. And by live, I mean work. If you're working in an industry space where you have limitless resources, then maybe you can do this. There's some ethical issues there as well. But anyways, we're going to assume that you have at least 1 GPU available and maybe not a whole, warehouse at your disposal. For efficiency, we're talking about essentially just the time required to draw samples from the distribution. We're assuming that this doesn't have an analytical solution. And we're also kind of assuming that the computational resources are not 0, but limited. So no massive parallelization allowed here. All right. Calibration, as I kind of mentioned, when you get a score out of one of these models that you then associate, you relate to a class, you want the score to match your intuition of confidence. And you want that to match regardless of the confidence level. So this is what we mean when we're talking about a well-calibrated model. If you have a score that comes out as small as 0.9, we'd expect 90% of the time for that to be right. Coverage. So if you have a single document and you predict the class, yes, you can get a single point estimate of this is the class I think it is, or you can create a credible set. And in your credible set, what we'd want is for that true value to be in that credible set at the alpha rate that you predetermine. So in this case, maybe nuclear fuels and material science constitutes your credible set. And so if the right answer is in there 95% of the time, you have coverage that is is well adjusted as well. All right, and last thing that I mentioned was the interpretability of this. So for a metric for measuring interpretability, it's the ranking accuracy. Is do the rankings of the predicted classes match what they should be for basically that article. So if you look at like similarity of different classes to nuclear fuels, you might say, all right, nuclear fuels being the right class, what is second most like nuclear fuels, atomic physics, third most like nuclear fuels, material science, arms control, down to cell biology. And so then we would then compare that to our predicted class probabilities and say, all right, well, how many of those ranks actually agree with what we're predicting? Okay, so previous work, and the previous speaker did an excellent job describing a lot of the previous research, the work in uncertainty quantification and neural networks. When we looked at it, we kind of disregarding approaches that included interpretability but didn't have uncertainty quantification. We kind of looked at it as, where do you want to incorporate your UQ into the architecture? While it sounds like a lot of fun to put distributions on every parameter in a full model, if you're working with large language models that are hundreds of millions, hundreds of billions of parameters, that might not be very practical. And so instead we kind of focused on, well, let's look at the output space and try to assign uncertainty to that portion of the model. And obviously why that's useful, it's a lot faster for these large neural networks. It can still lead to good calibration. But what we noticed was that there wasn't work done to investigate or enforce this kind of trade-off between calibration and good coverage, while also incorporating a sense of interpretability. Okay, so back to the framework of text classification. This is the general concept. You put in the document, you put it through your large language model, and you get out some embedding. At this point, your Z's are still continuous values, unconstrained continuous values. And then you put it through the softmax function to put the value between 0 and 1. Right? Now the softmax outputs are constrained to 0 and 1, but they, as I mentioned, just by their nature, do not necessarily mean a probability. And so that's what we're trying to kind of add in that aspect of it. And then from those probabilities, then you can predict what class the document came from. All right, so our work basically extended that belief matching. So the belief matching concept is to incorporate that into the training itself. Now they did it with on the last layer using a Dirichlet distribution to basically provide more stable optimization. We used Gaussian priors that we assigned to the logits layer before. And we use variational inference as a elbow loss function to then kind of optimize this problem. Now, the one thing I want to note here is that this construct is fairly flexible. There's no assumption of text data here or really any prior architecture, besides the fact that the assumption is that we're doing classification. And for more questions on the technical implementation of this, I would definitely direct them towards Dr. Hollis in the room. All right, so then we applied this to our data. We kind of had 3 experiments. The first one was on a subset of the OSTI data. That's a test set to run a little bit faster, essentially. So instead of using the full 60 labels for classes, just using 6. Nuclear fuels, nuclear fuel cycle, nuclear materials, material science, chemistry, military technology. And so with only 6 classes, it was easier for us to define a prior correlation structure. So we essentially had nuclear fuels and nuclear fuel cycle and nuclear materials as being highly correlated and the rest being essentially zero. And then we fit the model using the original belief matching construct, the correlated belief matching construct, and also comparing it to MC dropout as it's a standard approach. Okay, so what do we observe? So first, I want to note that in the level loss function, there are these hyperparameters that you can essentially tune. So you can tune them to achieve the balance that you want in these metrics. So since those parameters are adjustable, we decided we wanted to try to minimize expected calibration error, ECE, and then compare the other metrics across the model. So as you notice here, the ECE values basically tuned to be as similar as possible and being as low as possible. We report accuracy. The hope here is that the accuracy doesn't change drastically with this process, but that wasn't really the goal here to improve accuracy. What we were interested in is if we can tune EC to be low, can we maintain good coverage? Can we have interpretability and so a good ranking accuracy, and how quickly can we do it? So what we notice here is that, for coverage, this is, assuming a typical alpha rate of 0.05, the dropout actually did the best, but correlated belief matching was second. In terms of ranking accuracy, so the interpretability of it, this is where the model really shined, had significantly higher ranking accuracy than the other models. And of course, computational efficiency is where it proved its worth even further. Something like MC dropout, while it was good, that training process took in the order of an hour as opposed to less than a minute for correlated belief matching. The other thing that we notice is when you look at the plot here and you look at belief matching versus correlated belief matching, you notice the stability of this. If you want to tune this thing to achieve the balance that you want between calibration error and coverage, you can actually get your coverage to be closer to the optimal value without sacrificing too much in calibration error, as opposed to the belief matching construct where the calibration error jumped up pretty drastically. All right, so this is the subset. With the full OSTI data set, this is all 60 classes. First thing to note is that it's very difficult to specify a prior for 60 classes, a natural problem, but that's okay. We also developed a hierarchical correlated belief matching construct, which is the same idea where all you essentially need to do for prior specification is define a grouping structure. So these articles are part of a group. These articles are part of, or these classes are part of a group, I should say. And thankfully, the OSTI labeling system also provides that. It has the top level categories and then the subcategories. Of course, then the ranking accuracy metric is no longer applicable here. So we used group homogeneity. So essentially, how often are those similar groups in the category in your credible set? Okay, so again, we're trying to tune these things to have equal ECE, which close. Accuracy, again, about the same, not huge difference. Dropout still a little bit better. Coverage, dropout a little bit better. For grouping homogeneity, that though here we saw a twofold benefit almost in using the hierarchical correlated belief matching approach. And again, computational cost, this is a much faster method. And the same pattern for the trade-off between EC and coverage. The hierarchical correlated belief matching construct is more robust. Just for curiosity's sake, we also applied it to a different type of data to see how it would perform. So this is an MNIST fashion data set. So these are images, essentially images with 10 classes that are t-shirts, trousers, coats, bags. To define what is similar in this type of data, there's kind of a couple approaches that you could take if you wanted to get the full ranking accuracy. We were able to do that with an approach called word similarity that basically creates a metric for how similar the words are. And then that is used as your prior correlation matrix. But you could also then use grouping similarity if you wanted to and do the hierarchical correlated belief matching. Where then the groups would be t-shirts, pullovers, coach shirts, kind of being within the same group. All right, so what we notice again, you see tuned to be similar, accuracy here, almost no difference across the different methods. However, in this case, the coverage was actually best by correlated belief matching and also really close by hierarchical correlated belief matching, almost exactly at 95%. The ranking accuracy is still, that has been consistent, is the optimal with correlated belief matching. And of course, computational efficiency, all the belief matching approaches are faster. In this context, the hierarchical one was the fastest, and correlated belief matching ended up being third. Okay, so in summary, what have we done here? The purpose was to detect or triage information by pulling out articles that were relevant to nuclear research. And we did this with a domain-adapted language model, NucLM, which we found performed improved classification over off-the-shelf models. And we also found that this activity of pre-training, besides getting better performance, can also help mitigate some of the effects of small sample sizes. And then after that, we basically wanted to add better uncertainty quantification to the NucLM construct, and doing this with a prior correlation structure. In this particular problem, it's quite possible to define a prior structure for similar subjects in the scientific literature. And we were able to do so in a way that's computationally efficient, well calibrated in terms of error and coverage, and provides a nice way to kind of balance the two. And it's interpretable in terms of optimal class ranking. Okay, and I think I have a few more minutes. So question is then, so what? It's great that you can classify articles, whether in buckets of nuclear research or not, or various forms of nuclear research. How does this actually aid the problem of nonproliferation? Triaging the literature is basically the start, but scientific categories evolve, and then we might start to run into the out of distribution problem. And categorization alone does not characterize research. And so this is where, and this will be for a future talk, maybe if any of you are going to JSM and we talk about the second half of this. This is where we then go into topic modeling and link prediction. So we want to basically define what's in these subsets and actually try to predict future publications with context. So if we can put these articles through our model, through our NucLM model, get an embedding that defines what that article is about, subset it to the nuclear domain, and then you can kind of look at, here's a lower dimensional representation of the topic space for different articles. And you can say, all right, article or author 1 tends to live in this space, author 14 lives in that space. If we want to then predict in this graph, where is the next collaboration going to happen? A lot of research uses graph theory, uses the graph itself to predict the most likely connection between nodes. And so what we wanted to do was essentially say, we're going to do link prediction. We're going to say that, predict that author 1 and 14 are going to write a paper next, but we want to actually explain what that paper is going to be about. And that's what we're doing. All right, thank you.